Thank you very much, Roland. Thank you to the organizers for organizing this wonderful workshop here in beautiful Vienna, actually with a very sunny day today. Yeah, so I'm sorry for breaking the symmetry of the well-out schedule by appearing too late and not giving my talk on Monday. So this is everything I will talk about today is cooperation with Ettore Minguzzi from Florence. And maybe since today is Friday and everything else was talked about on Monday, let me recall real quick motivation for Gromov-Hausdorff convergence in Lorentzian geometry by recalling really quick what it means in the metric setting. So we start with two compact metric spaces, X and Y. And then there's a distance between these spaces defined by simply saying we're taking two isometric embeddings into a simultaneous, into a third compact metric space, and then measure the Hausdorff distance of the images. The Hausdorff distance is simply just the minimal radius of a set that contains the other set. And then you take the maximum of those two. That's a distance, and it's actually a theorem that this is a proper metric on isometry classes of compact metric spaces, because isometric spaces will not be distinguished by that. Okay, and what does it have to do with differential geometry? Well, metric spaces are sort of the atomic unit of geometry. So Riemannian metrics, of course, compact Riemannian manifolds are something much more regular, but you can give up regularity by turning a Riemannian manifold simply into a metric space by using the infimum of lengths of curves between points as a distance. This is classical that these are, this is a metric, and if your manifold, your underlying manifold here, M, is closed, then this metric will be complete. So the compact metric space. Okay, and what is the good thing about this Gromov-Hausdorff convergence in respect to Riemannian geometry? Because you're giving up regularity, you would think like, why would I care about these things? Well, it enables you to look at convergence of Riemannian manifolds even if there's a change of topology, for example. There's these classical examples of metrics on the three-sphere. You take this regular Riemannian three-sphere, and what you do is you make the Hopf vibration shorter and shorter, and then this, of course, it's a little bit of reflection needed to see that this will actually converge to CP1 with the Fubini-Studi metric. So actually the dimension can fall, but under suitable assumptions, like this theorem of Gromov is very classical in the field, you get good compactness properties under this Gromov-Hausdorff convergence. And this is and I've selected this particular theorem for this particular reason here, which I will come to next. So let me first recall what it is. You have a parameter R and a dimension n, and then you look at the isometry classes of metric spaces induced by Riemannian manifolds of bounded diameter, lower bound in the Ricci curvature, and fixed dimension. And this will be compact, has compact closure with respect to Gromov-Hausdorff metric on this space of the set of metric spaces. And the example I just mentioned with the collapsing of the Hopf vibration on this S3 exactly falls into the realm of this theorem. Yeah? Okay. And why is this so, or what was the consequence in Riemannian geometry of this theorem is the theory of Ricci limit spaces by Cheeger and Kolding, which actually then asked the questions, what do the limits of such metric spaces, do they have special properties? And they do actually quite a lot of special properties. They're quite regular actually, up to codimension 1 if you assume that the Ricci curvature here is always 0, for example. And then later, of course, with the theory of optimal transportation, the notion of synthetic Ricci curvature for such metric measure spaces with which came about, and which is usually attributed to Sturm and Lottin-Wieland. Yeah. Okay. So yeah, I drew your attention to this condition here with the Ricci curvature because in general relativity, these sort of formulations usually appear as energy conditions in your Einstein equations that you look at. So that's why basically this Gromov-Hausdorff convergence might be interesting to, or Gromov-Hausdorff theory, together with this Gromov compactness theorem, might be interesting to Lorentzian geometers or people interested in Einstein equations. But the big problem is you cannot just apply the metric Gromov-Hausdorff theory to Lorentzian manifolds, because intrinsically Lorentzian metric does not have a canonical metric associated with it. Yeah? Every choice of metric will be something, an additional datum that you invest axiomatically. And if you want to just look at convergence of, for example, solution of Einstein equations, then nobody tells you where that additional metric should come from, how you associate it in any particular way. So that necessitates to redevelop the theory of Gromov-Hausdorff convergence in the realm of Lorentzian manifolds or Lorentzian geometry. Nonetheless, even though you don't have a metric, you have something almost like a metric. Yeah, this is the time separation that we talked a lot about, everybody knows in the room. And it has one feature which it makes it very close to metric geometry that has a reverse triangle inequality. And you remember the definition of a metric space. There's not much besides the positive definiteness of the metric and the triangle inequality. That's basically it with what you have. So what you can do is, with the reverse triangle inequality, try to axiomatize your geometry using this. This is exactly what Ettore and me did with the definition of what is a bounded Lorentzian metric space. Here, bounded is not, you will see it in a minute, it's almost compactness, but not really compactness. Compactness is up to 1-point compactification. As a motivation why this is still a sensible approach, I would say always, this is not the final form of the theory. This is more like the local picture of what. Comparing compact metric spaces or Gromov-Hausdorff convergence of compact metric spaces to pointed Gromov-Hausdorff convergence of general metric spaces. Because in the end, we want spacetimes to be non-compact, so, but at least locally compact. So first, especially with view to the Gromov compactness theorem, in my opinion, it's important to first solve the problem locally before going over to non-compact manifolds. But anyway, so that's why where the bounded comes from. And we call them bounded Lorentzian metric spaces is a set X together with a function, which will play the role, of course, of time separation, which satisfies the reverse triangle inequality. Note that our time separation here is real valued, so we don't allow the value infinity. And that's the first point. The second point, yeah, so if you have metric spaces, you have naturally topology, because the metric just defines topology. And the topology is Hausdorff, for example. You know, very good properties and everything. In this setting, when you have only such a reverse triangle inequality, as you know, discussion of topology on spacetime has a long history. There's the Alexandrov topology, interval topology, these sort of things, which interact with each other for different steps on the causal ladder. Yeah? So our idea was to try to mimic something like bounded subsets of globally hyperbolic spaces. And this is what came out with its topology. So we assume that there exists a topology on X such that the time separation is continuous with respect to the product topology. And the sets which are at least epsilon separated in this, in the product or in the spacetime or in our bounded Lorentzian metric space, they should be compact for every epsilon. Yeah? I will give an example in a minute to see how, or to show how this works. Okay, and finally, we want in the end everything to be able to separate points with the help of the time separation. And this is just the separation axiom here. If you have two different points, there exists a third point such that either the time separation to the future or the past from X is different on those points or to the future. This is basically replaces the positive definiteness of the metric space. Metrics between X and Y is 0 if and only if the points are. Okay, so that is the definition. Changed a bit over the last half year. The first version of the paper on the archive had a different definition, but this is now the end result. Before I discuss especially the matter with the topology, which is sort of central to the entire discussion, let me really quick tell you a bit about related work and where all this comes from. This has a As you see, it has a long history. The first point is Herbert Busemann in '67. Herbert Busemann was a Romanian geometer who was studying isogeodesic spaces. So he was interested in spaces that have the same geodesics. For example, if you look at the Klein model of hyperbolic space, geodesics are straight lines. So it's exactly the same geodesics as flat space. And he tried to, after doing a lot of years of work on Romanian geometry, he tried to do the same thing with Lorentzian geometries, and he came up with a definition of what he called time-like spaces, which is sort of the first attempt, I would say, at axiomatizing Lorentzian geometry in a synthetic way. This is sort of synthetic geometry that we're doing. And later, 20 years later, 30 years later, came a Dutch guy, Noldus, together with an American mathematician or physicist, as I was told, Bombielli. And they wrote a couple of papers on Lorentzian spaces and Gromov-Hausdorff metrics. And the problem with those papers was that the community did not really accept the results or the validity of the arguments in there. So it was always a bit taken with caution what was written there. In the end, I have to say, when I look at the papers now, many ideas were already there, but he did not give any arguments why they should be true. Yeah. But still, he had the right ideas. And then it took another 15 years until Michael and Clemens came around with their Lorentzian pre-length spaces, which was sort of, I think, maybe Michael knows this better than me, was a sort of attempt to maybe amend the legs of this approach. Okay, and then Cavaletti and Andrea, they came up with a measured Gromov-Hausdorff convergence for Lorentzian pre-length spaces in 2021 on their preprint. And as Matthias told us on Monday, he and Clemens are working on in this direction as well. I will define in a minute what I mean by Gromov-Hausdorff convergence for this space. And of course, Olaf, last year, he wrote a very similar paper to ours, where he also defined Gromov-Hausdorff convergence and has a Gromov compactness result for Lorentzian pre-length spaces, as he told you on Monday, I guess. Yeah? Olaf, did you talk about that? Oh, yeah. I came late to the party, yeah. Okay, so let me comment a bit on this topology. So we assume in the definition there exists a topology. So there might be lots of topologies. Of course, I mean, if you have one topology that where something is continuous, a certain function, then of course, if you make the topology finite, it will stay continuous. So there are lots of topologies. But when you have such a condition of continuity, or as a cofinal topology, you can always take the intersection. And if you take the intersection, of course, the time separation will remain continuous. Also, this compactness property will remain true. And therefore, we can actually also just use this topology for the entire space. And we call this actually the topology that is associated to this X. We'll give you in a minute. You can also obtain this topology in different ways, but for the sake of the definition, this is maybe the right approach. There exists at most one space like infinity for these spaces. Yeah? One point, it's called here I0, which is null separated from every other point. By the separation property, there can be at most one point because this is not separate. If you have two of those, they would not be separated by our separation argument. So they play the sort of the role of the corner to the right in the Penrose diagram. If space like infinity belongs to our space. Huh? Yeah. Yes. Yeah. Yes. Yeah. And the compactness of these supersets, yeah. The super levels. Mm. Yeah, this is a sort of, it's not obvious, yeah. Yeah. But I will give you a theorem that will show you the one. Okay. So if this space like infinity belongs to the space, it is actually compact as a topological space. And otherwise, adding it artificially, just one compactifies your space. These are not so far off. And now to Patrick's question. You can consider the following Kuratowski type embedding of your space into the space of continuous bounded functions. You can take the d lower x, just denotes the point, the time separation from x in the first, and the upper index from the 2x. And then you can take a point and just map it to the tuple of those two functions. That gives you something in a product space of continuous bounded functions. The time separation is uniformly bounded. This is a consequence of the compactness axiom in the topology axiom of the definition. And if you put what topology you put on here, you put the topology of uniform convergence on there. And then what you can show is that this map I here is actually a topological embedding of your space in this. And that's sort of, that's another way to generate this topology. Okay, but all this together shows you that these bounded Lorentzian metric spaces are actually Polish. They are separable, complete, and locally compact. That's for the topology. Examples. Of course, there are the cosets that Sumati was talking about yesterday. Yeah? You take just a finite set, sometimes some function on there which is real value, non-negatively real valued, such that we have the reverse triangle inequality and we have the separation axiom. You don't need the topology because the topology follows actually from it. If you take this pair together with the discrete topology, then this is a bounded Lorentzian metric. This fits very well with everything. Second interpretation, yeah, this is, as you know, you can interpret these cosets as graphs with vertices and edges for every points that are positively separated. The second one is maybe to classical Lorentzian geometry is much more appealing. You take a bounded subset, a compact causally convex subset of a globally hyperbolic space. For example, your favorite causal diamond in your space. This is X, curly X. And this is not yet bounded Lorentzian metric space, but you have to eliminate sort of the space-like boundary from that thing. And this is basically in this picture here, these are these 2 points. When you delete them, this is D, then you get a non-compact bounded Lorentzian metric space with the induced topology. So you might, you might think the topology that we talked about is something exotic, but in these classical examples, or these standard examples like A and B, they are just the topology you would expect them to be. And now, Nicola. Because why do I insist on causal convexity? If you have something not causally convex, you might not be able to control this D set so well. Yeah? That you have to delete. Exactly. Yeah. I was not finished there. Yeah, X1 is just you throw D away, or X2 is just you collapse it to 1 point. This is basically the one point compactification. So, now the Gromov-Hausdorff convergence. The first definition of Gromov-Hausdorff distance in the metric case is the geometric one. The one I'm giving you now, the Romanian counterpart, is the one where you calculate with. This is a universal truth in mathematics. There are two types of definitions, the one you understand intuitively and the ones we calculate with. The second one is the one you calculate with. So how does it go? You take a relation between two bounded Lorentzian metric spaces, X and Y. Then a relation is simply a subset of the Cartesian product, such that the projection on each coordinate is surjective. And then you can define what is the distortion of such a relation by simply measuring how far the time separations between pairs of points which are in the relation, contained in a relation are. And this gives you if you take the smallest possible distortion, of such a relation gives you a Gromov-Hausdorff convergence between bounded Lorentzian metric spaces. And you can actually show that this is, again, this is an honest-to-God metric on isometry classes of bounded Lorentzian metric spaces. Isometry being here a bijective map that maps the time separations onto each other. It will be, it's not so easy. In the metric, with this definition, it's in the metric case, it's obvious that this map will be a homeomorphism. In this case here, it's a bit harder to show, but it's still true. No, they're not. Yeah. Because, well, first of all, that one is compact, that one not. Yeah. No, nothing. Yeah. It's completely wild as you want. Yeah. These are just the projections onto the first coordinate and the second coordinate. Yeah. Yeah. No, by this definition, I cannot take the empty set. Yeah. Yes, you have to imagine a picture like that. You take your Cartesian product, you have x here, y here, and then your R is something like this. But each projection has to be subjective. You have to sort of see everything. Okay. Yeah, so there was this Kuratowski embedding of your bounded Lorentzian metric space into this Cartesian product of continuous bounded functions. And that you can use that to actually define a metric on your bounded Lorentzian metric space, which we call the distinction metric. You can define it just axiomatically as I wrote down there. I don't need to have the pointer here, as I wrote down here. But it is actually also the pullback metric of the uniform convergence metric on the space of bounded continuous function on the space. So actually, the metric topology of this gamma here is actually the topology we started with. So we're not doing anything new. Funny thing is, it coincides with the Stong metric defined by Noldus in one of his papers. Olaf called that the Noldus metric. He defines it in a different way, but it's actually the same metric as you can show. It's a bit of like playing around with absolute values. But it took us a while to figure that out. Next nice feature of this metric is that the metric balls are causally convex. So if you have 2 points in a metric ball, then the entire causal diamond will be contained in there, which is sort of a nice feature. The not so nice feature is the following. If you take one of those causally convex bounded subsets of a globally hyperbolic spacetime, then there are no non-trivial rectifiable curves. This is really bad. I think Olaf has a comment on this as well in his paper. Yeah. But this sort of shows in a certain way that this metric is not the right one to do Lorentzian geometry with. It appears here naturally out of the time separation, but in the good examples, it's virtually useless. Yeah. Okay, maybe first results at the very end. I'm very fast. So you can define also Lorentzian length spaces with these things, with these bounded Lorentzian metric spaces. And if you have geodesics, you can use triangle comparison to define lower bounds on sectional curvature. And this is actually preserved under this form of Gromov-Hausdorff convergence that defines by the metric. Yeah? Yeah. Any sort of bounds. Yeah. And second, we can use this distinction metric to define the usual notions of what is a uniformly totally bounded family of bounded Lorentzian metric spaces. And we find actually that this is compact with respect to the Gromov-Hausdorff convergence. This is the first half of Gromov's compactness theorem for the lower bound Ricci curvature Riemannian geometry. The second part of that theorem is just an application of Bishop-Gromov inequality. The problem here is that the distinction metric that is used here to define these things doesn't talk to the Lorentzian geometry in the same way as in Riemannian geometry. The Bishop-Gromov inequality is there to translate volume into distance, or the other way around, distance into volume. Here, it's not so obvious if you try to apply this in the Lorentzian. But nonetheless, the hope is, of course, that with some other definition of these things, one will be able to either find a better version of Bishop-Gromov inequality for these spaces. I know there exists a lot. Andrea there has written quite a few things, or a different metric has to be invented to a different approach to these sort of things. But if that happens, we have a theory of Ricci limit spaces, and that would be quite nice. If you take those results, these regularity results in Chico coding as a blueprint, it would be quite nice to have something similar. Yeah. Okay, I think, yeah, that's it. Thank you very much.